Hello, good time of the day. Welcome to my talk. Today I'm going to be talking about building petabyte scale machine learning models using Python, specifically TensorFlow and PyTorch. Um, Before we get started, just a quick introduction. My name is Vaibhav Srivastav. You can call me VB. I have spoken at PyCon Korea before as well. In fact, last year I gave a workshop as well as a talk. Throughout this talk duration, if you have any questions and whenever you're watching this talk, feel free to tweet out to me at the rate reach_VB. If you want to find my blog or if you want to find my email ID, you can go to vaibhav.blog. You would find the information on the bottom left about my Twitter handle as well as my website. Now, without further ado, let's get started. Um, Now, before we get started, I want to try something new here, right? So, before we begin the actual talk, I want to spend a minute and I want to convince you why distributed machine learning is something that you should be passionate about, is something that you should be excited about. For that, what we did was we ran a couple of benchmarks on TensorFlow and PyTorch, both on CPU as well as couple of GPUs for an image classification task. Now, what we did for this task was we took the CFAR 10 dataset. This dataset, mind it, has roughly about 10 classes, some 60,000 odd images. And what we did was we provisioned an N1 standard 4 instance on Google Cloud Platform. And you can find the hardware details down below. We also provisioned a couple of GPUs, which were NVIDIA Tesla T4. And the intention was that we'll run multiple experiments by changing the number of workers, by changing the number of GPUs, changing the number of CPUs, and then measuring how much of a time difference or how much of a speed up difference does the code actually get. All right, let's go to the results. Now, after running multiple such experiments, we found that both for TensorFlow as well as for PyTorch, right, the overall speed up when you're training the model, right, is increases manifold times as you increase the number of workers, right? Now, specifically in the case of both in the case of TensorFlow as well as in the case of PyTorch GPU, on your left, you would see that the overall speed up relative to one worker, meaning how much time would you spend while you're running your entire machine learning modeling exercise on your own laptop or just on one worker. If you compare that with running the same exercise with multiple workers, you would see that the overall speed up is manifold times more than what it should be, right? What it should be when you only have one worker. And you would see that the overall speed up is pretty much the it follows the same trend across CPU as well as GPUs, right? What that tells us is as you increase the parallelism, as you increase the distribution in your overall cluster, your overall time to train your machine learning model decreases, right? And you can also get the same inferences from the graph on the right as well. The graph on the right talks specifically about two key parameters, right? The first one is the compute. That is that how much of my overall clocks are being put into training my model. Second is communication. How much of an I/O overhead do I have between my workers or between the data set and my overall training exercise, right? And you would see clearly that as we increase the number of workers, both the overall communication overhead also decreases, as well as the overall number of the overall time taken to achieve 80% accuracy, meaning the overall time taken for the model to become 80% accurate on the data set also decreases, right? So this is a clear case for building distributed machine learning pipelines. If this looks a bit confusing to you, bear with me for a couple more minutes. I'm just gonna get into demystifying this entire stuff. But I wanted to start off and give you like a real life example of how much easy does your life becomes when you build a distributed machine learning pipeline, and when you train it, when you train your models at scale. They not only run faster, they also execute your entire pipeline in a much faster fashion, and reach the benchmark accuracy in a more faster way. Just a quick thing. All of these benchmarks were taken from ML Bench. ML Bench is a joint initiative with PwC, Google, a couple other academic institutes as well. You can find the link to that on the bottom right. So just click on that and you'll be able to get both the code as well as the benchmark results as well, and a detailed explanation of how those jobs were run and what actually happened around those as well. All right, now that you've got a bit of feel of what distributed machine learning can do, let's go through let's go through the agenda real quick, right? So today we're going to be covering like 6 key things. First, we're going to be talking about why do we need distributed machine learning. We're going to get a broader intuition of how distributed machine learning works. What are different types of machine learning? Distributed machine learning. Then we're going to be specifically talking about out-of-core machine learning, which is a type of distributed machine learning. And then we spend a bit of time talking about how do we actually build these scalable machine learning workflows, right? And do some sort of discussion around what sort of frameworks, TensorFlow, Dask, PyTorch, what should you use in order to be able to build those scalable machine learning workflows. Last but not the least, my favorite part, we're going to be doing code walkthrough. We're going to be talking Python. We're going to be talking TensorFlow, and we're going to be going through both of these frameworks. And I've prepared some sweet Colab notebooks for you that you can use and leverage later on when you're building your machine learning pipelines. Then towards the end, we're going to finish up with some sort of questions and answers that you can put on the comments, or you can tweet out to me on my tweet handle on the bottom left side. Cool. Let's get started. So first of all, why do we need distributed machine learning, right? While we answer this entire question, let's take a step back, right? And let's look at how a typical machine learning exercise look like, right? In a typical machine learning exercise, you would have some sort of data, right? This data can be images, can be text, can be audio signals, can be anything like that, right? And you would have some sort of a task to do with it, right? You would have a task like, for example, classification, or you would have a task like regression or forecasting, something like that, right? Let's take an example. Say you have a box full of balls, right? So a simple classification task in that would be that you take all the balls of red color and put them into another box. You take all the balls of blue color and put them into one different box, right? That's basically classification, right? So you're classifying your data. So you have some data and you have a task to perform with that. Simple. Now, how do you actually train a machine learning model to learn that task, right? You would have some sort of an algorithm which would be consuming this data and would be churning out your entire task. Now, for a very simple classification example, let's take the balls example itself. For that example, you would have some sort of a model like logistic regression, or say a neural network, or naive Bayes, some sort of an algorithm like that, right? To sort of take the data that you have and classify that data. For that, in case of regression, you would have either say an ARIMA model, or say a linear regression, or random forest regression, decision tree regression, all sorts of things that are present right now. Bottom line is, for a given data and for a given task, you would have a model or some sort of an algorithm solving for X, right? And then you would have for this model to be able to give you the best possible results, you would have some sort of a loss criteria or some sort of an optimization criteria. Now, what this optimization criteria effectively would be is is that this loss criteria would tell you that at what point in your equation plane, at what time, at what point in the entire plane of your n-dimensional data, where exactly is do you get a curve, or do you get like get a surface that best describes your entire data, right? So in a two-dimensional plane, that can be y is equal to mx plus c. So how do you get that? Is by finding the exact equation of that line wherein the overall loss from where your data is the least, right? So you have some sort of a loss function. In like a regression scenario, you would have something like mean squared error, or r square score, or RMSE, something like that, right? So you have a loss function. So again, you have the data, you have a task, you have a model, and then you have your loss function. Then like like what function do you have to minimize, right? You know what function do you have to minimize. Then you would have some sort of an optimization procedure, right? In a very simple neural network, you would typically use something like either gradient descent or stochastic gradient descent, wherein you're taking small steps across the plane of your data, and you're trying to see what's the value of your loss there, right? If your loss is very low, then you say if your loss is lower than the previous loss, then you say that this is a step in the right direction, right? So you keep on traversing through all the curves, all the data points within your data set across n dimensions, and that's how towards the end, when once your loss starts plateauing to a particular point, then you know that this is the most optimal plane, or most optimal equation for representing your data, right? So again, you have the data, you have the task, you have your model, you have your loss criteria, and you have your optimization procedure, right? So far so good. A very simple neural net, or a very simple machine learning model, which is performing a task that you've given to it, right? Now, all the way up until here, let me go back. Now, all the way up until here, everything's good, right? You can read your data into pandas. You can import some sort of a library, say scikit-learn. You can import, say, random forest or decision trees, build your model, look at the overall evaluation, and you're good to go, right? And this kind of setup would work all right. And effectively, right now, you won't see a need for distributed machine learning. So then why do we actually need machine learning? Why do we actually need distributed machine learning? We need it specifically in cases wherein you have massive data scale, or you have massive model scale. And in the third case, maybe you just want efficient computation of your algorithms. Maybe you have a very complex optimization strategy, and it takes a lot of time, and you want to divide that across a couple of machines to be able to reduce that time. So let's spend a minute on this slide, right? So what does massive data scale mean, right? So one of the first things is that when we talk about data scale, it is very relative, right? What I mean by that is for a computer, or for a laptop with 16 gigabytes of RAM, 32 gigabytes of data is something which is big data, right? Which is massive data for a laptop with 16 gigs of RAM. Whereas for a Raspberry Pi with just 1 gig of RAM, or with just 2 gigs of RAM, even like a 4 gigabyte of data would be very huge. So your massive data scale depends upon what kind of a machine, or what kind of a cluster are you running your analytics pipeline, or your machine learning pipeline on, right? Similarly, model scale can also have multiple meanings, right? So a model can be big. Say for example, a neural network can be, say, 500 megabytes in size, or say in 1000 megabytes in size. Actually, you know what? Let me go back. Sorry. So when we talk about massive model scales, effectively, these like what we mean by a massive model scale is the overall architecture of your model itself, right? So for example, when we talk about, say, naive Bayes, or say random forest, or decision trees, those are actually quite small models, right? Why? Because those are effectively bunch of mathematical equations and their corresponding values in an overall weighted circuit, right? Um, Weighted graph. Whereas when you talk about, say, something which is as complex as, say, for example, neural collaborative filtering, or say convolutional neural networks or recurrent neural networks, then those models would have your overall embedding of the data itself, as well as the weights for individual nodes on the architecture itself, which would sometimes correspond to massive data sizes, right? What those model sizes. Those model sizes could be 1 gigabyte, could be 10 gigabytes, or in case of, say, some models that you see right now, like GPT-3, those could be like of the order of couple you know of the order of tens or twenties of gigabytes as well, something that does not even fit in your RAM as well. So in those scenarios as well, you would need distributed machine learning so that you can infer out of that model itself, right? Then comes the third one, which is efficient computation of your algorithm, which is, say, for example, if you're running across massive data, and you have a very large architecture, then you would need a mechanism to be able to execute your algorithms in the fastest possible manner, right? In the most efficient manner, wherein you're utilizing maximum of your existing resources without overburdening them, or without creating a bottleneck in between two processes. And that's where efficient computation of algorithms comes into place, right? This can be something as simple as, if we take our case of balls again, right? So say, for example, if you have one box of balls, right, and you want to segregate red and blue into two different boxes, then one scenario can be that you are the only one who's segregating those balls. Whereas in a second scenario, you can ask a friend of yours, and you can say, hey man, can you help me? Can you take half of these balls and can you separately segregate them into red and blue? Now, what you've effectively done is you've reduced the overall workload on yourself, and you've added another person to help you out with with the task of segregation, and that's actually gold mine, right? Why? Because one, you've reduced the load on you, which means that you will be able to complete your task in roughly x by 2 time, where, and at the same time the other person is also doing the other half of it. So what that means is you've effectively halved the time that you were previously taking, right? And that gives you speed up. That's the most simplest case of distributing a task. So that's distributed machine learning 101 for you. Moving ahead, if we go like more detailed, if we go into more details about how this actually works, is by like what we just, like the example that we just spoke about. That's something which is out of core, which is called out of core ML. What out of core ML does is it is basically an algorithm which uses external storage, and essentially what it would do is it would train your model on small chunks of data, right? So let's take a different example now. Say, for example, you're building a forecasting model for your stock prices. Say you want to model the stock prices of Tesla, right? Now you would take past a couple years of Tesla prices, right? Say at a minutely level, right? That gives you like very large data frame, right? That now you have to train an overall forecasting model on, right? So what you do is you divide the overall data set into multiple chunks. You take 1 year of data first and you train your model on that, right? You persist the weights of that, and then for the second year of data, you start training from those weights, and you train on those weights. Then you repeat this process for the third year of data, for the fourth year of the data, for the fifth year of data, and so on and so forth, right? What this helps you do is it does not overwhelm your overall architecture, right? And it would effectively help you run or help you train models on very large data sets as well, right? And you can easily parallelize these tasks as well, right? Because more often than not, these can be independent tasks. So you can independently train 12 different models on 12 years of data, and then you can combine their weights and come up with some sort of averaged model on top of that as well. So that's what out of core ML is, which means that effectively, instead of loading the entire data set into your RAM in one go, you only load some bit of data first, and then you divide and conquer that. So I hope that gives you good enough details on what out of core ML is, because that's what we're going to build on in the slides to come. Now, let's go back to our drawing board, right? We spoke about we spoke about having a data set, having a task, having a model, and then a loss function, and then having some sort of a optimization function on top of it, right? Now, let's take that example and let's add the mix of distributed ML on that, right? So if we were to distribute the overall task, as we said before, into two different nodes, how would we do that, right? You would, first of all, at the ground level, right, you would partition your data into two sets, right? You would have a data set partition 1 and you would have a data set partition 2, right? Your task remains the same. If it's classification, it remains the same. If it's regression, it remains the same for both the partitions, right? What changes is that, except like previously you were running that task or say classification on the entire set of data, now you run it on a smaller partition of data, right? Your model remains the same again. So if you were using a convolution neural net before, again you would use the same CNN, same architecture across both the partitions, right? Your loss function updates, right? And this is kind of obvious. Why? Because your loss function earlier was giving you the value of your loss for just for the entire data set, but now you're training your entire model on a partition. So now you need to have a loss that is computed on that partition itself, not on the entire data set. So loss function gets updated. Also, your overall optimization strategy would also be updated. Why? Because now you need to, even though you're training your models into two silos, right? But you still need to optimize it to get one global minimum, right? One global minimum. And the simplest way of doing that can be that you have an f1 of x, or like whatever optimization value that you get, you add for both the partitions. And how this will be achieved is through like having some sort of communication and complexity, and basically having like a synchronous communication happening between the two data sets. It says that, hey, I just finished say x data points and these are my weights, so why don't you look at this, and say that, hey, I just finished this and these are my weights, and so on and so forth. So a communication keeps on happening between the two. And that's how that's the simplest way of building a distributed machine learning pipeline, right? If I was to scale this up, I can have n number of data partitions working on n number of worker nodes, right? Running effectively the same code, except running it on small chunks of data, and then I aggregate their overall losses to get the best possible manner. So again, this does the same thing, right? It reduces the overall time for running your machine learning models. Not only that, it also helps you get from your data all the way till insights as soon as possible, right? Now, enough like theoretical stuff, right? If we were to do this in action, how would we do this, right? In real life, you could do it in two ways without going into too much details, right? The first one would be, if say you're familiar with scikit-learn, the first method would be to use something known as partial fit, right? You can do like a model.partial fit. What partial fit does is it effectively helps you build incremental models. So it isn't parallelizing your task, but what it's doing is it's giving you the capability to train a model on larger data sets, larger than your RAM data sets, um, on your laptop or on your virtual machine, whatever it may be, right? And this is particularly useful if you're already familiar with how DaskML works or how scikit-learn works and so on. So this would follow the same kind of methodology. In fact, scikit-learn has a couple of models which support partial fit. And again, what this would do is it would take small chunks of your data and sequentially train your model on those small chunks and then aggregate the overall weights and aggregate the overall equations, your final equation on the base of on the basis of that. For example, there is a stochastic gradient descent regressor, a stochastic gradient descent classifier in scikit-learn which supports partial fit as well. So you can use that, and effectively you can train a machine learning model on a data set of size 32 gigabytes with just a RAM of 8 gigabytes as well, because it will take only say 4 gigabytes chunk in one go, process them, and then take the next 4 gigabyte chunk, take the next 4 gigabyte chunk, and so on, right? So this will never give you out of memory error, right? The second way, which is something which I personally recommend as well, if you're starting off from scratch, is to do a graph-based model training, right? Now, what a graph-based model training is that you use something, say, like TensorFlow, PyTorch, MXNet, Dask, some sort of a distributed library, right? And what these libraries do is they build a directed acyclic graph of your entire pipeline, right? So it would put all your pre-processing functions, your model functions, your optimization functions, your loss calculation functions, all in like one graph, right? And it would help you get that graph, optimize that graph for your entire architecture, for your entire cluster architecture, right? And then run your training jobs. What this effectively does is it would help you optimize all the nooks and crooks in your entire architecture before it actually starts training. And second, this way you can run it on multiple different machines. So you can effectively achieve parallelism in some tasks as well, right? And that's where a lot of like TensorFlow, PyTorch stuff helps, right? And that's what, if you remember in the first slide, that's what we were discussing as well. When we were running multiple the same task on multiple worker nodes, it was quite easy. Why? Because it like the overall code was written as a directed acyclic graph, right? So it was already compiled, and then like all it was happening was it was executing on different GPUs, and that's why we were getting a speed up. But more on this later, and in fact I have a working session just discussing these in detail as well. Now comes the $1,000,000 question, right? How do we build these scalable ML workflows given whatever knowledge we have, right? So I would say like there's something for everyone. Let's talk about like in this particular area, right? There are generally just two scenarios, right? First scenario is wherein you as a data scientist or as a machine learning engineer, you have written code in say scikit-learn, stats models, XGBoost and the likes of it, right? And you're very well aware about building machine learning workflows on that, right? That will be scenario one. Scenario two is and again, like assuming that you already have a pipeline written in all of this. Scenario two is where you're starting an experiment from scratch, wherein you're building a machine learning model from scratch, right? In those scenarios, you're free to choose a particular framework. You're free to choose say TensorFlow. You're free to choose something like that. What you would typically do in both of these scenarios is something like this, wherein you already have, say for example, if you already have an entire pipeline, like in an existing setup, if you already have a machine learning pipeline written in scikit-learn, or say in XGBoost or some sort of a library like that, then you wouldn't want to like recreate that library, right? You would want to make sure that your entire code is maintainable and you want to make minimal changes to it. In those particular scenarios, what you could do is something which is put on the left, is you can use Dask for creating batches of your data and then building like incremental pipelines either using Dask ML or using scikit-learn, right? Both of them are pretty interoperable, and you can use them to build your distributed pipeline, right? And this way, you don't have to make a lot of changes into your existing workflow, and you would also get some sort of benefits of your um, of distribution and out of core ML into your pipeline. Right. Second is a scenario wherein you're like starting from scratch and you're like building an experiment from the get go. In those scenarios, I generally recommend going with either TensorFlow or PyTorch or MXNet, one of these libraries wherein you can effectively create an end-to-end architecture, and the library itself would create a DAG for you, and then you can use different distribution strategies across your cluster to be able to build those models, and those are again like very easy to maintain. The only thing is it will take some bit of time for you, if you're new to it, to get a hang of it, right? And again, now like with TensorFlow 2.2, there are like multiple new APIs that have been introduced, like for example tf.data, tf.distribution strategy, tf. It supports both eager execution and also like the lazy load execution, wherein you create the entire graph and then run it, and that's I think the way to go if you have new experiments to run. Now enough talk, let's code. So now that we've gone through such a detailed demo about both TensorFlow as well as Dask, you may have a question about which framework, or like which flow should you use for your next machine learning project, or for taking on or sort of maintaining your existing machine learning workflow, or something like that. Truth be told, this is one quote by Thomas Sowell, which I follow to the core, which is that there are no solutions, there are only trade-offs, right? For example, if you were to build something with Dask, then you're stuck with possibly less parallelizable code, right? Whereas if you were to build something with TensorFlow, then you're stuck with a very huge learning curve in terms of learning TensorFlow. It's numerous APIs, not to mention different sub libraries for image, for text, for audio, and all the other stuff that it comes with. Also keeping in mind that the overall TensorFlow, PyTorch, Dask, all of this entire family is something which is rapidly evolving as well, right? So you have to keep yourself up to date on that. However, one quick thing that I would say is, and which we have covered before as well. Remember the two scenarios, and there's something which I always put out is, if you already have a machine learning workflow which is written, say in scikit-learn or say in Dask, and you want to extend it to work on possibly larger set of data, then you should possibly look into using Dask ML, right? Because you don't have to rewrite from scratch, right? You can use the existing pipeline, albeit make some changes here and there, and you're good to go. Your pipeline works on a much larger chunk of data then. However, if you were to build something from scratch and you know for a fact that you'll be using, say, big data, again, relative to whatever cluster or whatever machine you're running your data in, you may want to use TensorFlow from the scratch, or you may want to use, say, PyTorch from the scratch. I prefer TensorFlow, to be honest, but that helps you bake scalability right from the scratch into your project. So that's what my recommendation would be. And again, do go through the links to the Colab notebooks that I just showed a while back. You can easily retrofit those to work with your data sets and try them out for yourself as well. With that, thank you so much for attending my talk. I hope I added some value to your knowledge base, and you learned something right out of it. Again, you can reach out to me for any questions at the rate reach underscore VB. You can find my previous talks at webof.blog. And I look forward to hearing from you. Thank you so much.